Alright, so we've all heard of black holes, right? If you have, but
You know nothing, Jon Snow.
you're in the right place. Visualizing a black hole can be difficult, in part because of its extreme physics that tend to go against our conventional wisdom or how we think the universe should behave. The best way to imagine a black hole is to imagine a tear in the fabric of space, whose gravity not even light can escape. But to better understand how something like a black hole can even exist, we'll have to dive into the formation process, and it involves the stars. So a star, like our sun, seems to shine nice and bright indefinitely. But how? The light we get from the sun is the result of quadrillions of hydrogen nuclei smashing into each other to create helium, a very rare event in and of itself. As hydrogen atoms fuse into helium nuclei, they lose a little bit of mass as they release electrons. Multiply that little bit of mass by the quadrillions of times this reaction happens throughout the core, and you end up with approximately 4 million metric tons or 8 billion pounds of matter that gets converted into energy every second. That's the energy flowing outward from the sun's core. This is what we call nuclear fusion. One way to visualize the sun's nuclear fusion is to imagine a bunch of nuclear bombs inside the sun constantly going off every second of every day. And just like an exploding bomb, the sun's constant release of energy creates tremendous outward pressure, like a grenade in a box, that relentlessly tries to expand and spew its contents outward. So with all that energy pushing outward like a bomb, you're probably wondering why stars just don't explode right away, right? Well, that's because while the outward pressure is pushing out, an opposing force is trying to pull everything in. That force is gravity. Since we know gravity comes from the mass of an object, while the pressure of the bombs are pushing outward, the gravity created by the mass of a star is trying to pull everything inward. This balance or struggle between outward and inward forces is what we call hydrostatic equilibrium. And it goes on throughout the lifetime of the star. Fusing every element results in mass defect, which essentially means the product of the reaction has less mass than the reactant. When iron is fused, the star's core loses energy, which leads to a rapid cooling of the core, resulting in immediate loss of pressure. This loss of pressure means the tug of war between pressure and gravity comes to an end. Gravity overcomes the now weaker outward force and starts to contract, speeding the gravitational collapse to its core. Iron fusion essentially means game over for the star. Here's the crucial determining factor to whether or not a star becomes a black hole. If the star is approximately less than 20 times the mass of our sun, it blows its outer layers in a huge explosion, leaving only a core of about 20 kilometers in diameter, and possibly resulting in a neutron star or a white dwarf, depending on the actual mass. However, if the star is bigger than about 20 times the mass of our sun, gravitational collapse overcomes any resistance as it rapidly shrinks, preventing that outward pressure from bouncing back out, and instead continues to force the star to shrink into an infinite point in space. This is a black hole, a now dead star packed into a tiny point in space so immensely dense whose gravity not even El Chapo could escape. But you need not worry, folks, our sun will be around way after we're all gone. It's projected to burn nice and bright for another 6 billion years or so before its complete demise. I hope this video is somewhat useful to you guys, and if it was, my name is Jose. If it wasn't, my name is Peter. Either way, you should think about subscribing. Thank you for watching.